In this video we'll be talking about Venn diagrams and tree diagrams. Starting off with Venn diagrams, they look something like this. And so this diagram here can be used to work out the probability that event A happens, event B happens, event A and B happen at the same time, or neither event A nor B happen. There's a little bit of set notation that comes along with tree diagrams. So for instance here, we have A union B. It looks a little bit like an upside down U, but it's not exactly the same thing. It doesn't have like the little tail on it. And the union is going to be the probability that A happens, B happens, or A and B both happen, which is represented by this part of your diagram. So anything that lies within this bubble, or both. And then this is A intersection B. And this is the probability that A or and B happen at the same time. So the part that overlaps between the two events. And then this is like not A, which we call the complement. So A and then a little dash above it will mean that anything that doesn't lie within A, which is represented by this part of your diagram. So anything that lies within the event B bubble, but not in the intersection here, and then not in the just A part. Anything that lies outside of this circle is the complement of A. You should find an example, make it a little bit more clearer. So I have a class of 10 students, 3 have a dog, 4 have a cat, 1 has both. I'm going to start off by drawing a Venn diagram to represent this scenario. So this here I'm going to call having a dog, and then this will be having a cat. Usually when you're in Venn diagrams it's easier to start off with the middle part and then work outwards. So I know that one student has both a cat and a dog. So in this section here we have 1. And then I know that 3 students have a dog, so there's going to be 3 students inside this circle here. But I've already got 1 in here because I have a cat and a dog, so I'm going to do 3 take away 1 is 2. So now you can see I've got a total of 3 students that have a dog, 1 having both, 2 having just a dog. And then you can do the same thing for cat. So we have 4 students having a cat, 4 minus 1 is 3. So therefore the number of students that have a cat and just a cat is going to be 3. And then I need to work out how many students don't have a dog or a cat. So we've got 2 plus 3 is 5, 6. So 6 students have one or the other or both. We've got 10 students in the class, so therefore 4 must not have a dog or a cat. Now I can use this diagram to work out some probabilities. Find the probability that a student has a dog and a cat. So let's use proper set notation. This is the probability D intersection C. So the overlap. Students have dogs and cats, that's this part here. And that's 1 over 10 because there are 10 students in the class. Find the probability that a student has a dog or a cat or both. So this is the union between having a dog and having a cat. So the students that have a dog, have a cat or have a both. So probability of D union C. So this is going to be 3, 4, 5, 6, which I can simplify and make that 3 over 5. Find the probability that the student does not have a dog. So this is the complement of D. So anything that doesn't lie within D. So this is these students here don't have a dog. These students here also don't have a dog. But these students do have a dog, so I won't count those. So 3 plus 4 is 7. You could have worked this out a slightly different way, so because probabilities always add to 1, this also applies here. So we could write the probability that a student does not have a dog. Dog is the same as 1 minus the probability that a student does have a dog. 1 minus, and then we can look at how many students have a dog. That's 3 of them. 1 minus 3 over 10. which would still get me to my 7/10. This is a bit more long-winded in this example, but you might need to use this principle in future. If for some reason you can't work out the complement straight away from the diagram, you might need to use 1 minus the probability that it did happen. Okay, you can have a go at one yourselves now. So this time we have a class of 30 students, 10 students study maths, 22 study English and 6 study both. First off, draw a Venn diagram. So like I said before, it would be easiest for you to start off with the students that study both and then work your way outwards. And then you have some probabilities here to find out. Try and use set notation and then work out the probability. So if you pause the video now and then have a go at that question. So here's your solution. You should have a Venn diagram that looks something like this. So I've called my events maths and M and E for maths and English. Your Venn diagram looks like so. And then here are your probabilities. The probability that a student studies maths, the probability that a student studies maths, English or both, the union. The probability that a student does not study maths or English, this is the same as the complement of the union. So if this section here is the union, if I take the complement, then it's anything that doesn't lie within this part, so therefore the outside bit. Or you could have written it like this, so it would be the intersection between students that don't study maths and don't study English. So the students that don't study maths is this part. This obviously includes some students that study English, but if I look at the intersection, so where does this overlap with students that don't study English, which is all of this part, my overlap is just going to be the outside. And then the probability that the student does not study English, so anything that doesn't lie within E, so 4 plus 4, that gets you 8/30 or 4/15. If you haven't simplified them, that's fine, because I didn't say you had to, so if you've left them out of 30, that's all correct. Moving on, tree diagrams. So I have a bag of counters, 3 are black, 2 are red. I remove a counter, I take note of the colour, I replace the counter, and then I repeat a second time. We can draw a tree diagram now to represent this scenario. Here's my little bag of counters, 3 black, 2 red. So when I take my first counter, there's 2 possible things that could happen. Either I select a black counter, or I select a red counter. The probability that I select a black counter is going to be 3 out of 5. 3 black counters, 5 total. And then the probability that I select a red counter is going to be 2 out of 5. Now depending on what happens here, I can go and take a second counter. So if I take a black counter originally, I put this counter back, so I'm still going to have the same scenario again. And again, I can either select a black counter or a red counter. And my probabilities will still be the same, because I've still got 3 black out of 5, and I've still got 2 red out of 5. If, however, on the first occasion I selected a red counter, when I put that counter back in, I've still got the same number of counters, and then again I can still go on and select a black counter or a red counter on my second go, and I've still got 3 out of 5 black and 2 out of 5 red. Now, hopefully you can see we've now got 4 different possible outcomes that could have happened once I've done both trials. So I've either selected 2 black counters, or I've selected a black counter and then a red, or I selected a red counter first time and then a black second, red black, or I selected red red. And I can work out the probability of any one of these scenarios happening. The way I do that is by multiplying down my paths here, like so. That's usually how we work out, that's always how we work out the probability that one event happens, and then another event happens as well, is you multiply these 2 probabilities together. So we've got 3 over 5, multiplied by 3 over 5, gives me 9 over 25. So this is the probability that I select a black counter and then a black counter. And then I want to work out the probability that I select a black counter then a red counter. So 3 over 5 times 2 over 5. So that's 6 over 25. And then if I carry on, so if I select a red counter first, that's 2/5 multiplied by 3/5, 6/25, and then red, 4/25. Because we've got 4 possible scenarios that can happen, what you should find is that if I add all of these probabilities together, I get 1. So if I add 9 plus 6 plus 6 plus 4, I get 25/25, which is just 1. If you don't add these up and get to 1, then you've gone wrong somewhere. You need to go back and check. Now we can use this tree diagram to work out probabilities of various different events happening. I've got some examples here. So work out the probability of both counters are black. This is probability that I get a black counter and then a black counter. Well, I've already done that. So there's only one way that I get black, and that I must have gone down this path here. So 3/5 times 3/5, which is 9/25. So the probability that I get black is 9/25. And then I want the probability that at least one counter is black. So to get at least one counter black, I could have got black, or I could have got red, or I could have got red, black. Do you see how in any one of these scenarios we have at least one black? I've got a black there and a black there. Here I've got both, but that still counts as having at least one. So therefore I'm going to have to add together these probabilities. So I'm going to need to add together black, red, because I get a black counter here, and then also red, black, because each of these 3 scenarios give me at least one counter being black. So the probability to get at least one counter being black is 9/25 plus 6/25 plus 6/25. 12, 11. Sorry, 21. So if I add together all these 3 probabilities, then I get 21/25. And this is the probability that I have at least one black counter. And then we can use the same method for the counters being different colours. So if I go back here and go, okay, what scenario do I get counters being different colours? Well, not here, because they're the same. However, I will get counters being different colours here, because I get one black, one red. And I also get counters being different colours here. Again, this case is not part of my scenario. So for the probability that counters are different colours, I'm going to have to add together these 2 to get 12/25. And we've worked out probabilities. Okay. Very similar example, slightly different scenario. So I've got the same bag of counters again. I'm going to take a counter, I'm going to take note of the colour. This time I do not replace my counter. So I'm going to take my counter out, I don't put it back in the bag, and then I'm going to take a second counter. So again, we could either get a black counter or a red counter on the first go. The probabilities here are going to be the same. So I take a black counter with probability of 3/5, and I take a red counter with probability of 2/5. However, when I come on to taking my second counter, these probabilities now are going to depend on what happened on the first go. So if I follow down this path here, then I've already taken a black counter. So what that means now is down this path my bag's going to look like this. I'm going to have one black counter less. So now I've got a total of 4 counters, 2 being black and 2 being red. So therefore the probability that I now take a black counter on my second go is going to be 2 black counters, because I've got 1 less black counter, out of 4 because there are 4 total counters. See if you can pause the video here and fill in the rest of this tree diagram. Okay, hopefully you've had it go. So if you take a black counter on the first go, then you've got 1 less counter here, we've got 4. You've still got the same number of reds, so you should have 2 over 4. Or we could write this as 1 over 2. This would be 1 over 2 as well. If I come down and I take a red counter first, then it means I've got a bag that looks like this now. So the probability that I take a black counter is going to be 3 over 4. And then the probability I could take a red counter is going to be 1 over 4. And now you can multiply down your paths to work out any of your scenarios. So either I get black black, or I get black red, or I get red black, or I get red red. And then you can multiply down your paths to work out the probability that each of these happens. See if you can do that now if you haven't already. And then work out these probabilities, same as before. So work out the probability that both counters are black, at least one counter is black, or the probability that counters are different colours. So pause the video and have a go. Okay. I'm going to do it slightly quicker this time, hopefully. So the probability we have both counters black, we want the probability of black black. All you're going to have to do is multiply down this path here. So you've got 3/5 times 1/2. Which is 3/10. And then the probability that at least one counter is black. So what scenarios do we get one counter being black at least? So it's either this one, or this one. So anything but this path here. Because anything but this path here, if you remember, all of these add to make 1. So what you could do, you can either multiply along these paths to work out all 3 and then add them together, add together these 3 here, or you could do 1 minus this path here. So the probability that at least one counter is black is going to be 1 minus the probability that both counters are red. So 1 minus the probability that both counters are red is going to be 2/5 times 1/4, so that's 2 over 20. 1 over 10. 1 minus 1/10 is 9/10. The probability that counters are different colours, so that is going to be these two added together, because here we've got different colours, here we've got different colours. However, in these two scenarios we have the same colour. So we've got 3/5 probability of different colours. So the probability that we get black red is 3/5 times 1/2, 3 over 10, plus probability of red black is 2/5 times 3/4, 6 over 20. Some quick mental arithmetic. So we've got 3 over 10, so that's the same as 6 over 20. 6 over 20 is 12 over 20. 20. Or 3/5. Okay, thank you very much. I hope you understand everything. Have a good day.